Part 2. Calculating magnetic fields of electric currents. Now we know how to find the direction of magnetic field produced by different current configurations, and we will know how to find its magnitude, which is also called field strength, or simply field for short. The SI unit of magnetic field is Tesla. Below are some of the order of magnitudes of common magnetic fields. A. Magnetic field around a long, straight, current-carrying wire. The field's strength is directly proportional to the current but inversely proportional to the distance from the wire. It is given by the formula here, where B is mu log I over 2 pi r, where mu log is called permeability of free space, which has a value of 4 pi times 10 to the power negative 7 Tesla meter per ampere. From the equation, we can see the magnetic field B is directly proportional to the current, while inversely proportional to the distance r from the current carrying wire. When two wires carry the same current flow, the magnetic field combined and the following shows the direction of magnetic field around them. First of all, it is the upper wire current, which flows from left to right, that produces a magnetic field that points outward above the wire and points into the paper below the wire. Next is the current that is flowing in the lower wire, that also produced a magnetic field that points outward above the wire, but then into the paper below the wire. And you can see that the magnetic field in the middle cancels each other, so that there is almost no magnetic field between the wires. In fact, for the magnetic field outside of the two wires, the magnetic field is 2 times the magnetic field that is produced by the single wire. So the magnetic field changes gradually from out of paper to 0 in the middle to into the paper from top to the bottom of the diagram. Indeed, we may show the situation by using dot and cross symbols, and the two currents are represented by 2 crosses on the left, and the magnetic field is drawn this way. You may also represent the situation using 2 dots, as seen from the right instead. In example 4, 2 wires carry the same current placed side by side, results in a neutral point between the wires, similar to figure 4.2J above. Obviously, the 2 wires must have the current flowing in the same direction. When currents are in opposite directions, there will not be any neutral point between the wires, but there will be neutral points on the 2 sides instead, as shown here. B. Field inside a long solenoid. The magnetic field B inside a long solenoid is given by the following formula: mu log Ni over L, where capital letter N is the total number of turns and L is the length of solenoid. Hence, we may also express it as mu log Ni, where the small letter n equals capital letter N over L. That small letter n is the number of turns per unit length, or simply turns density. Obviously, the magnetic field is directly proportional to the current I and the turns density, small letter n, but independent of the radius of the cross-sectional area of the solenoid, and hence independent of its radius. In example 5, how different factors may affect the magnitude of the magnetic field inside a solenoid is discussed. Now try checkpoint 3 on the next page.